Hi everyone, welcome to Beyonds, and today I'm going to walk you through your first chapter that's on real numbers. So I've divided the way I see this happening is I have divided this into two parts. One is the first part that deals with your Euclid's lemma and a few other concepts, your HCF, LCM, etc. And the second part works with your rational and irrational numbers. So, without much ado, we'll dive into the first topic. Now, what are rational numbers? What are real numbers? If you see, real numbers are anything that you can sort of visualize around a line, visualize on a line. For example, they could be whole numbers and integers, or they could be decimals, or they could be some form of rational numbers such as fractions or decimals or something of that sort. Or you could even have irrational numbers, which are, for example, pi, root 2, etc., root whatever, square root of any positive number. All that could also be visualized along line, and all that would fall as real numbers. If you see over here, there would be a difference when we go into the rational and irrational numbers. That's where I would bring this out. Pi would be an irrational number, but 22 by 7, which is nothing but pi, is going to be a rational number. So anything that can be described in form of a p by q form is going to be a rational number. And anything, because even your 0.125 could be described as something like 125 by 1000, so that's going to be rational number. And anything that cannot be designated as p by q tends to be an irrational number. Now, some of the examples of numbers that would not be classified as real numbers would be infinity, or would be some imaginary numbers. That's the reason, while talking about real numbers over here, I said square or cube root of any sort of some nth root of any positive number, not negative number. If you have any negative number, that's going to be an irrational number. Sorry, that's not even going to be a real number. So nth root of any negative number is going to be a not a real number. Now, that's a very generic overview on real numbers, but what we're going to particularly deal in case of real numbers is Euclid's division lemma. That's something that we're going to see right now. Fundamental theorem of arithmetic. We're going to see prime factorization, and then we're going to see how to find HCF and LCM using prime factorization. Now, what is Euclid's division lemma? So, Euclid's division lemma says that if you have any two numbers, say a divided by b, such that it leaves a remainder c, then you can always sort of express this as a is equal to b into, say, some number q plus c. All right, where c is always if a number such that 0 is less than or equal to c, which is less than your b. Why is that? Let's consider this. Let's consider a number such as 220 divided by 3. How would you describe that? So in this particular thing, this is a remainder, this is the number, this is the quotient, sorry, this is the divisor. So now 20 by 3. So how would you find, 3 6 are 18. So you have 3 into 6 plus 2. That's what your 20 is. Now this is going to be true always, irrespective of what number you take. You're always going to have this remainder as something that's going to be greater than or equal to 0. Or in case you have like 18 divided by 3, this would be 0, and in that case it would be equal to 0. But otherwise, this remainder would always be a number that's less than or equal to 0, which is less than or equal to your main divisor. And that's because the moment this becomes greater than divisor, you did something wrong. You could have just increased the quotient here by 1. So, for example, instead of this, if I had taken this as, for example, instead of this, I had expressed this as 20 is equal to 3 into 5 plus 5. Now you would say, here it is, it's bigger. But I just made a mistake over here. I could have taken another 3 over here, and it would be 3 into 6 plus 2. So if you are at any point of time able to write it in this form where your r is greater than your divisor, then that means you've done something basically wrong. So that's what Euclid's division lemma says. Let me just get this all off so that you can concentrate on what's there on the screen. But Euclid's division lemma basically says that given any two positive integers a and b, when a is divided by b, then there's always an integer q and r, which basically makes it as a is equal to bq plus r, where 0 is less than or equal to r, which is less than or equal to b, less than b. And you have to remember, this is nothing but remainder here in this case, and q is nothing but quotient. Why am I saying this? Because now you will realize that, give me 1 second, now you will realize that this is nothing but your normal long division. This is how you would have normally done long division. So if you had done 5, 2, and 7 divided by 5, you just found 20 and you got 1 over here. So that itself shows 1 is less than 5. 17, 5 3s are 15, 2 again remainder, 2 is less than 5. So that's how it always goes on. Now using this, there are a few problems in your textbook that maybe a few of them we could look into. Now let's look at this particular question. A trader was moving along a road selling eggs. An idler who didn't have much work to do started to get the trader into a wordy duel. This grew into a fight. He pulled a basket with eggs and dashed it on the floor. The eggs broke. The trader requested the panchayat to ask the idler to pay for the broken eggs. The panchayat asked the trader how many eggs were broken. He gave the following response. If counted in pairs, that's in twos, 1 will remain. If counted in threes, 2 will remain. If counted in 4, 3 will remain. If counted in 5s, 4 will remain. If counted in 6s, 5 will remain. If counted in 7s, nothing will remain. My basket cannot accommodate more than 150 eggs. So how many eggs are there? Okay. Now, just first of all, consider these statements. This is nothing but something that you can formulate in the form of your Euclid's lemma equation. That's basically there's a number called a, sorry, give me 1 second. Yeah, there's a number called a, which can be given as or shown as 2b plus c, okay, where c is going to be 1. And c is equal to 1. This is going to be shown in a is equal to 3b plus c, and c is equal to 2, so on and so forth. You can write equations like this. So that's what I've shown over here. These statements can be sort of like written in this form. A is equal to 2u plus 1, a is equal to 3t plus c. And if you notice, we've used different u's and t's there because we don't know what the quotient is going to be. We do know what the remainder is going to be. We do know that it's the same number of eggs, so we can use a everywhere. We don't know the remainder because that's already given to us over here. So that's the 1 that I've used over here, the 2 that we've used over here, the 3 that we've used here, 4, 5, and 0, because nothing is remaining over there. So that's how this will go. And once we've written down this equation, we also know that the basket cannot accommodate more than 150 eggs, and that when counted in sevens, nothing will remain, which means that the number whatsoever it is lesser than 150, and it is perfectly divisible by 7. So if you find all the numbers that are perfectly divisible by 7, what would we get? We would get some numbers such as 7, 14, 21, 28, 35, and a list of these numbers. Now, if you go back, you will also notice if counted in 6s, 5 will remain, right? So now we've got to see what are those numbers that when counted in 6s will provide 5. So if you see, based on the division of 6, the following numbers can be shortlisted because we know 6 5s are 30, right? 6. So 6, this is just going to leave 1. 6 ones are 6 and then 1. 6 twos are 12 and 2. 6 threes are 18, that's going to leave 3. 6 fours are 24, that's going to leave 4. 6 fives are 30 plus 5. So this is going to leave you 5, right? And similarly, all this is going to have the same problem. 6 sevens are 42, that's perfectly this thing. 8, 9, 10s are 60, so 3, 66, 6, yeah, so here 72, so that's going to leave another 5, and that's the similar thing with 119. So you know about 6, these are the 3 numbers that you can shortlist from there. And then the next thing we hear is, if counted in 5s, 4 will remain. So out of these 3, what are those numbers when they're counted in 5, 4 would remain, and that's just 119. If you count 35 and 5, 0 would remain. If you count 77 and 5, 2 would remain. And if you count 119 and 5s, then 4 would remain. So the answer is 119. So that's how you could use Euclid's lemma to solve this particular problem. There are different ways to solve this problem, but that's the way we are using it in this particular instance. Now, let's get into a little more meatier part, how to find HCF of 2 numbers using Euclid division lemma over here. So prime factorization would be the easiest way, but we have got quite a few proofs and quite a few things that you could explain using Euclid's lemma. So it might come as some amount of explain how this could be done, or why this is true. Something of that sort of proof could come through. So find the smaller number of the two C and D. So how would you find the HCF of 2 numbers, say C and D? You would have to find the smaller of the two C and D, and then if, for example, you find that D is smaller than C, then you would have to explain or write C in a form such that C is equal to dq plus R, which is basically a Euclid's lemma. And if R is equal to 0, you have to solve this such that if R is equal to 0, then you know that D is the HCF of C and D. But if it is not, then you will again have to write this equation in a form such that D is equal to this particular your lower HCF, lower of the 2 numbers, is equal to the remainder into some quotient plus another remainder. So that's D is equal to RS plus T, and you continue going down like this till the remainder becomes 0. Let's look at a problem of that. Here's the one. Show that every positive even integer is of the form. So that's what I said. A lot of proofs of this sort could come during the exam. Some have come in the past papers. So show that every positive even integer is of the form 2q, and that every positive odd integer is of the form 2q plus 1, where q is some integer. Now, how are you going to do this? As per Euclid's lemma, you know that A is equal to BQ plus R, right? You know that A is equal to BQ plus R. This is your basic Euclid's lemma formula. You know that for this, 0 has to be less than or equal to R is less than or equal to B. Now, if you consider that A is equal to 2q plus R, then your R has to be either 0 or 1, since R has to be lesser than your B, and this is your B in this particular case. So R is lesser than B. So it has to be 0 or 1. So A is either equal to 2q or A is equal to 2q plus 1. Now, if A is equal to 2q, then A is an even number because 2q is surely divisible by 2. If you divide 2q by 2, you just get q. But if you divide 2q plus 1 by 2, 2q is divisible by 2. Hence, 2q plus 1 is not an even number, it's an odd number. And that's why we say that every positive odd integer is of the form 2q plus 1, where q is some integer. So that's how we go around proving this particular theorem. Now, you could get some problems like these as well. A sweet seller has 420 kaju barfis and 130 badam barfis. She wants to stack them in such a way that each stack has the same number and they take up the least area of the tray. What's the number of barfis that can be placed? I think I forgot something over here. So it's going to be, what's the number of barfis that can be placed in each stack for this purpose? So Now, how would we go around doing this? We know that the sweet seller has 420 kaju burfis and 130 badam burfis, and she wants to stack them in such a way that each stack has the same number of same number of burfis, and they take up the least area of the tray. In which case, the height of each stack should be as high as possible. So, what you want to actually find is the highest common factor. That would be the number of burfis that would go in each stack. Say there is a stack like this. Each stack, what would be the highest number of burfis that go in each stack, so that this particular area, because the stacks have become so big, this particular area becomes the smallest. Right? If this was, if in the other hand we tried finding the smallest stack, then we would get the largest area. Right? So that's what the idea is behind this particular problem. Now we do know that 420, we do need to find the HCF of 420 and 130. We do know that we would have to write 420 is equal to 130 into Q plus some form of R, where R is going to be less than 130. Now if we do that, we do know that 420 is equal to nothing but 130 into 3, that's going to be 390 plus 30. Right? So we just found that there is a remainder here, so we've got to solve it further. So that's going to become 130 is equal to 30 into Q plus R. That can be written as 130 is equal to 30 into 4 plus 10, right? And then that can be further written as, since we have this number, that can be written as 30 is equal to 10Q plus R, which is nothing but 30 is equal to 10 into 3 plus 0. Hence, what's the HCF? There must be 10 sweets in each stack. So you're going to have, that's your HCF. So you're going to have 10 sweets in each stack. So you're going to have 13 stacks of badam barfi and 42 stacks of kaju barfi. That's going to make a total of 55 stacks with 10 pieces each. So that's going to be the solution to this particular problem. Alright, let's go to the next one. The next question is basically an army contingent of 616 members is to march behind an army band of 32 members in a parade. Now let's just hope that my solution doesn't come here. But basically what it says is there are 616 members in an army. And they're going to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. So this is the army contingent, and there's an army band that's consisting of 32 members. This is going to walk in a particular number of columns, say 3 columns over here. So the 616 would also have to walk in the same 3 columns. And what's the maximum number of columns in which they can march? So again, we're going to find the highest common factor between 32 and 616, so that the contingent can sort of march past behind the army band without and the number of columns stand the same. So that's going to be the solution. We need to calculate the HCF of 616 and 32. How are we going to do that? We're going to say 616 is equal to 32 into Q plus R. Now we do know, let's do a long division, we'll see that (32 2s are 64), so can't go that way. So that's done. And then this is going to be 320, so this is going to be around 9, right? So that we would have true. So that's going to be 32 into 19 plus 8. So the remainder is not 0. This is not equal to 0. Hence, what we would have to do is write 32 is equal to 8Q plus R, which we know is 8 4s are 32. So R has become 0. So we know 8 is the maximum number of columns because that's the HCF basically. This is the HCF. 8 is the maximum number of columns. So you would have around 4 rows. So when you see, you have 1, 2, 3, 4 rows with 8 columns. 1, 2, 3, 4, 5, 6, 7, 8. And similarly, you would have your something like this would be your, oh, I think I made a boo-boo here. Yeah, so this is going to be your give me one second. This is going to be your army band, and then behind this is going to be your contingent in again 8 columns. All right. So this was your solution to that particular problem. Let's go to the next problem. The next problem is use of Euclid's lemma to prove something. So use Euclid's division lemma to show that the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. How do we go about that? Now, as per Euclid's equation, a number can be explained in the form a is equal to b cube plus r, which is what we have said over here, and 0 is less than or equal to r is less than or equal to b, is less than b. So, so since a has to be 3, a needs to be some form of 3, 9. So let's consider that a is 3 in this particular, or b is 3 actually. B to be 3. I made a mistake there. B to be 3. So a is equal to 3 cube plus r, where r is 0 or 1 or 2. Now, if a is equal to 3 cube plus 0, a cube is nothing but 3q cube, which is a cube is equal to 27q cube, which is a cube is equal to 9 into 3q cube, which becomes 9m. So cube of any positive integer, which is basically a over here, is of the form 9m. Now, we could also have consider, now let us cube a is equal to 3q plus 1. A is equal to 3q plus 1. A cube can be taken as 3q plus, give me one second. Yeah, I don't want to distract you all. So, now a cube is equal to 3 cube plus 1. 3 cube plus 1, so that's going to be 3 cube plus 1 whole square, whole cube. That's 27q cube plus 1 cube, so a cube plus b cube plus 3ab into a plus b. Right? What is this? What is your a plus b whole cube is equal to a cube plus b cube plus 3ab into a plus b. That's what I've written over here. So 3 cube is 27q, so a cube, that is 27q cube, plus 1 cube, that's your b cube, 1 cube, plus 3 into 3q, that's a into b, into 3 cube plus 1. That gives you 27q cube plus 27q, 3 3 is 9, 27q square plus 9 cube plus 1. And then you can take out 9 from a lot of these things and see that this is going to be 3q cube plus 3q square plus q plus 1, and that's 9m plus 1. So that's your second number over here, right? And the third number is, what if it was 3q plus 2? Then you're going to have again the same formula. So you're going to have 3q plus 2 cube. That's going to be 3q cube plus 3 into 3q into 2 into 3q plus 2 in sorry, that's going to be plus, not 2. So plus 2 cube. So that's 27q cube plus 54q square. 3 3s are 9, 3s are 27, 2s are 54q square plus 3 3s are 9, 2s are 18, 2s are 36q plus 8. So that can be written as, you can remove the 9 from everything over here, and that becomes m, so plus 8, hence this can be proved. This is where your Euclid's lemma sort of becomes a little important when you're trying to find such proofs during your examinations. Now, what's fundamental theory of arithmetic? Every composite number, that's what it says basically. The fundamental theory of arithmetic is either a number is prime or it's composite. Now, every composite number can be explained as a product of primes. Now, what does composite number mean? Composite number, the word composite itself means that it is comprised of something. It is made up of something. And that's what's happening over here. So, for example, you have a number called 66. 66, now if I see over here, 66, what is it made up of? It's made up of 2 into 33. It can be written as 2 into 33. 33 can be written as 3 into 11, and 11 is a prime factor, so 11 is just going to go once through 11. So any composite number, so a number is either primary or composite, prime or composite, and if it is composite, then you can always express it as a product of primes, and the factorization is unique, but the order need not be unique. For example, I could always write 2 into 3 into 11 is equal to 66, and 2 into 11 into 3 is equal to 66. So at that point of time, don't say that this is not unique. This is unique in the fact that you can never write 66, you can never factorize 66 in any other form apart from 2, 11, 33, and 11. So you cannot write any other, you cannot find out any other new prime factors for this, but you can always change the order of factors however you want. That's the same true with 105 over here. You see it can be explained as 5 into 7 into 3, and that's true. It can, how much of you break it down, you could maybe write a 1 in front of it, but that's about it. You can't do anything else with it. So this is true of any number. Now we could always say, for example, that's what I was trying to explain over here. 400 can be written as 400 is equal to this particular, give me 1 second. 400 can be written as this. You could always say 400 can also be written as 10 into 4 into 10, but in that particular case, 10 and this 10 are not exactly not prime, right? So what your fundamental theory of arithmetic says is that a composite number can be explained as a product of primes, product of unique primes, and the factorization is pretty unique. So this is what's going to be a deciding factor when determining what's the HCF or LCM for a particular number. Now let's take a problem for this. I think I'm on the right page. Am I? Yes, I'm on the right page. So consider the number 4 raised to n, where n is a natural number. Check whether there's any value of n for which 4 raised to n ends with the digit 0. That's a question, right? So I'm pretty sure most of you would know this, but let's just go through it anyway. So, and now if any number ends with, so for any number to end with 0, end with the digit 0, okay, it would have to be divisible by 5. You take it anyway, 2 into 5, 5 into 2, 5 into 4, 5 into 6, it would have to be divisible by 5. Okay, so now 4 raised to n, it actually would have to be divisible by both 5 and 2, but in this case, since it's 4 raised to n, we already have a 2. We could always write it as 2 square n, or 2 raised to 2n, or 4 raised to n. Either way, we already have that. So all we need to do is make sure that it's divisible by 5, and if so, then it can be sort of like ending with the digit 0. Now, if you see 2 square, we know that since it's 4 raised to n, it has to be 2 raised to 2n. So 2 squared is 4, 2 cube is 8, 2 4 is 16, 2 5 is 32, 2 6. So irrespective of what your n is, or it can never be, and it could even be a 0. Okay, so 2 raised to 0 is 1. But whatever your n is, it's never going to result in a number that can give you a number with 0. And therefore, there is no such value of n for which 4 raised to n will end with a 0. Take 2 square, 2 cube, 2 4, 2 5, 2 6, 2 raised to 7, 2 raised to million, whatever you take, it's never going to end with a 0. It's always going to end, if you see this pattern repeats, it's 4, 8, 6, 2, 4, 8, and if you actually take 2 raised to 8, it's going to be that's it. Again, it's going to see result in 6 and That's it. It would just go 4. So the pattern is 4, 8, 6, 2, 4, 8, 6, 2. That's how it keeps on going. It would never end with 0. So that's what this particular problem is about. Now comes the interesting part. How to find HCF and LCM using prime factorization. Now, prime factorization is basically your basic the basic theorem of arithmetic that we just discussed. Any composite number can be displayed or described as a product of prime factors, and the prime factors that come in it would be pretty unique. The order might not be unique, but they would be pretty unique. So, so when you are trying to find the HCF, what you need to remember is HCF, that's the highest common factor. It's nothing but a common number between two numbers, say A and B. When you're trying to find HCF, what are you trying to find? You're trying to find a common number C, which would perfectly divide A, giving a remainder 0, perfectly divide B, giving a remainder 0. So now if I could explain A as, say, P into Q into R, and B as, say, M into N into O, then in order to find the HCF, I would have to find the smallest power of common factors between A and B. For example, if I know that I don't have M and N over here, but I rather would have so let me say I have P and Q and I have O, then the HCF would be P into Q. However, if I had P square on both sides, then it would be P square into Q. So that would be the highest, because you're still trying to find the highest common. So it's going to be the smallest power of each common prime factor. If, for example, if I had this, give me 1 second. Yeah. If I had it in this way, then this would be so basically you get the idea. So the HCF would be P into Q. That's it. So it's going to be the product of the smallest power of the common factors which are common amongst two numbers, while LCM is going to be the product of the greatest power of each prime factor involved in both the numbers. Right? So basically it's going to give you a least common multiple. LCM stands for least common multiple. It's going to give you the you're going to find it by finding the greatest power of all the prime factors shared by both the numbers. All right. So and another formula that you could use over here is LCM is equal to product of the two numbers x and y divided by HCF. I'm sorry about that. Cut that. Another problem that you could use over here is HCF and LCM can always be found by considering this particular formula over here. LCM of two numbers of x and y in this particular case is equal to product of the two numbers x and y divided by HCF of the x and y. Remember why I have said this x and y over here is because this is applicable to only two numbers. If you have three numbers, don't apply this. Three numbers, don't apply this. It's going to be wrong. LCM of three numbers into HCF of three numbers is not equal to the product of three numbers. We'll try figuring that out in a few problems. Now find the HCF of 96 and 404 by the prime factorization method, hence their LCM. Now I like to do it this way, even though it was a little bit difficult for me to write over here, but I like to generally do it this way. So you have 96. 2 4 is 8, 2 8 is 16, 2 4, 2 1. So basically how many times, so what I'm trying to figure out over here is how many times give me 1 second. Yeah, let me figure it out for you. So 96 has to be divided by 2. We know it's ending in 6. It has to be divided by 2. So it's 2 4 is 8 and 2 8 is 16. Now 2. This is again divisible by 2, because if it's ending with the 2 4 6 8 or 0, it has to be divisible by 2. So 2 2s are 4, 2 4s are 8. Again this is ending in 4, so it's divisible. 2 1s are 2, 2 2s are 4. Again, it's ending on 2. 2 6 are 12. That's 2 3s are 6. 3 1s are 3. So that's 96. And 404 would be 404. 2 2 2s are 4. 0 2 2 101, and that's it. 101 would be just that one. So basically, this can be written as 96 is equal to 2 raised to 1 2 3 4 5 into 3, and 404 is equal to 2 square into 101. So if I were to find the HCF is equal to product of the smallest power of common prime factors. So what are the common prime factors over here? That's just 2. 3 is not common amongst these. 101 is not common. So 2 raised to the smallest power of amongst smallest power of the common factor amongst these two values. So that's going to be 4, and LCM is going to be the greatest power. So you're going to raise the joint prime factors to the highest power that's possible. So that's going to be 3 into 101. That's 9696. So that's what your HCF and LCM is. You could also find it this way. So instead of doing it that way, because that's another way that they've asked for, LCM is also found as 96 into 404 divided by 4. So 101, 96 into 101 is nothing but 9696. Yep. All right. Now to continue, next problem is going to be find the HCF and LCM of 6, 72 and 120 using the prime factorization method. So that's going to be pretty straightforward. 6 is nothing but 2 into 3, right? 72, now 2 is there, so this can be divided by 2. 3s are 6, 2 6 are 12. Ends in 6 can be divided by 2. Ends in 8 can be divided by 2. 9 is a factor of, 3 is a factor of 9, and here you have 72. And 120 is also 2. Ends in 0 can be divided by 2. Ends in 0 can be divided by 2. Ends in 0 can be divided by 2. Well, 5 ends in 5 can be divided by 5, and that's it. So now you could write these as basically 6 is equal to 2 into 3. 72 is equal to 2 cube into 3 square, and 120 is equal to 2 cube into 5 into 3. So now HCF is nothing but the smallest power of common factors. Now what's common amongst this? 2 and 3 are common. 2 and 3 is here, 2 and 3 is here, 2 and 3 is here. So that's going to be 2. That's the smallest power of 2 amongst all these 3 numbers. And 3. That's the smallest power of 3 amongst all these numbers. And a funny thing is I've written 5 over here, but figure that. It's 2 into 3. So that's going to be 6. That's going to be 6. And then LCM is going to be 2 raised to the highest power, that's cube, into 3 raised to the highest power, that's square, into 5. So that's going to be basically 8 into 9 into 5, that's 40 into 9, that's 360, and that's right over here. So that's what your actual numbers are going to look like. So now that we've solved that, let's get to the next problem. Now this is just me trying to prove that the product of HCF and LCM of 3 numbers is not equal to the product of those 3 numbers. So for example, if I take product of 6, 72 and 120, that's divided by HCF of 6, 72 and 120, that's actually 6 in this particular case. What you're going to get in this case is 6 into 72 into 120. So divided by 6, that's going to be just 72 into 120. But we know for sure that the LCM is nothing but 360. So 72 into 120 is going to be way bigger than 360. So that's why I said that product of 3 numbers is not equal to HCF into LCM of those 3 numbers. Now going to the next one. Find the LCM and HCF of the following pairs of integers and verify that LCF into HCM is equal to HCF is equal to product of the 2 numbers. So first we have 26 into 91. We could always explain that as 26 is equal to 2 raised to 1 into 13 raised to 1. 91 is equal to 13 raised to 1 into 7. Now the HCF would be the smallest part, that's 13, of the common factors. So common factor is only 13. The smallest part is 1, so it's going to be 13 raised to 1. LCM is going to be the highest power of all the factors between these two numbers. So that's going to include 2 into 13 into 17 into 7. 7 raised to 1, 2 raised to 1, 13 also raised to 1, since we don't have a higher power. So that's going to be 182. Now we could always try proving this. That is 26 into 91 divided by 13. That's nothing but 13 2s are 26, or 13 7s are 91, and if it's 13 7s are 91, then that's going to be 182 again. So original LCM that was calculated earlier. Another this thing is prime factors of 510. So 510 is, so 2 2s are 4, 2 5s are 10, 2 5s are 10, so 5 5s are 25, 5. So that's going to be 3, and that's going to be 7. So that's 510 prime factorized for you. And then you have 92, so that's going to be divisible by 2, divisible by 2, and that's just 23, right? So these are the prime factors that you see over here. And we know that HCF is the highest factor, or sorry, lowest factor of the common factors between these two numbers. That's 2 is the only common factor, and the lowest factor part is 1, so it's just 2. And LCM is going to be the highest power of all the factors between these two numbers. So that's going to be 2 into 5 into 3 into 17 into 23. The only difference being that it's going to be 2 square, because that's the highest power over here. So that's going to be 23460. You can actually, if just let me know in the comments if you want me to show these multiplications to you as well during the problem, because I'm assuming you could pause it and try doing these calculations yourself, because nothing works much better than doing the numbers with your own hands. But if you want me to show these numbers, these multiplications, these divisions in detail, let me know in the comments, and I will go ahead and work on that in my next video. Now this is going to be, so now let's try to prove that LCM into HCF is equal to product of two numbers. So LCM is equal to product of these two numbers, that's 92 into 510 divided by 2, that's nothing but 255. Let's multiply that. Plus 9 5 is 45, 5 4, and that's how we get this particular value, right? So hence we've proved this. Another one that's coming along is how are you going to solve this one? Let me erase this so that I can have some empty space to show you all the calculation for this. Okay. Now, 336 ends in 6, divisible by 2, ends in 8, divisible by 2, ends in 4, divisible by 2, ends in 2, divisible by 2, and divisible by 3, and then divisible by 7. This is 336, and 54 is that can be basically explained as 2 into 3 cubed, that's what 54 is, and 1 2 3 4, 2 raised to 4 into 7 into 3, that's what your 336 is. So HCF of 54 and 336 is going to be common factors between both these numbers are nothing but 2 and 3 raised to the lowest factor. Lowest factor of 2 is 1, lowest factor of 3 is 1, so that's 6. And LCM is going to be the common factors between, or all factors between these two numbers. That's 2 into 3 into 7 raised to the highest numbers possible. So highest pass possible. So 3 is raised to 3 amongst these, and that's 4. And that's nothing but 16 into 27 into 7. And that's basically 3 into 0, 3024. I'll let you do the calculation. And here I am proving that this particular proof is true. Again, this is pretty similar to our 4 raised to n. Can that end? So check whether 6 raised to n can end with the digit 0 for any natural number. So basically it's pretty similar to our 4 raised to n. Can it end with 0 for any natural number? Basically 6 raised to n is nothing but 2 into 3 raised to n, and for it to end with 0, it had to have 5 in it in some way. Since it does not have 5, what would happen is you would have 6. So if n is equal to 0, you would have 6 raised to 0, that's 1. N is equal to 1. Always it would end in 6. It would never end in 0. So hence it cannot end with 0. So that's the solution to that one. And I think this is like the second last problem that we have. Explain why 7 into 11 into 13 plus 13 and 7 into 6 are composite numbers. So basically, what did we say? Composite numbers, any number that can be written as a product of prime factors, and that would constitute unique set of prime factors that would constitute as a unique number, or as a composite number. So in this particular case, you could always write 7 into 11 into 13 plus 13 as which is nothing but into 77 plus 1, 78. 78 can be factorized as so basically your 7 into 11 into 13 plus 13 is now equal to 13 into 13 into 3 into 2. So it is a composite number. And similarly your 7 into 6 into 5 into 4 into 3, 5 can be written as 5 into which is nothing but, how would we explain this now? Let me remove this so that we have some place to solve this problem. Now you know 7 into 6, 7 6 are 42. Okay, 4 3s are 12, 2s are 24. Oh, 2s are 24. Multiply this. 4 2s are 8, 4 4s are 16, plus 2 2s are 4, 4 2s are 8, 1008 plus 1, that's 1009, so 5 into 1009. So since this has more than 2 factors, it's a composite number. Now there's a circular path around a sports field, and Sonia takes 18 minutes to drive around one round of the field, while Ravi takes 12 minutes for the same. Suppose they both start at the same point and at the same time and go in the same direction. After how many minutes will they meet again at the starting point? So now what you're trying to figure out is what would be the least time in which they would meet again. Considering that both of them are running in the same direction and have started at the same time, right? So for that, you need to find what's that one least number of minutes in which both Sonia and Ravi would have maybe cover different number of circles, but would have actually completed the circles without any remaining time, without any remainder. So basically what you're trying to find is LCM, right? So to find LCM of 18 and 2, you would have to prime factorize 18 and 2. 18 is equal to nothing but 2 nines are 18, so 3 square, and 12 is nothing but 4 into 3, so 2 square into 3. So your LCM is nothing but 2 into 3, and everything raised to highest power, so that's this, 36. So they're going to meet in 36 minutes after Sonia takes around 2 rounds and Ravi takes around 3 rounds. So that's the solution to this problem as well. Let me know, that's the end of our class for today, but let me know how the problems were. Let me know if you want me to deep dive into a particular problem. If you find a sum as very difficult, put it on the YouTube comment section below. Put the sums explanation or sums problem statement, and I will solve that for you. I will walk you through it in another video and post that as a comment in the comment section. So let me know how you find this video, and thumbs up if you really like it, and follow us again at beyonds.org, where we have a set of questions for you, a sample test that you could take to see how far you've understood this particular lesson. Thank you, and have a good day.